Well, hello everyone and welcome to today's session. As a courtesy, let me remind you that if you have questions, please make sure you post them on the chat or raise your hand by selecting the participants tab. As you may know, plant pathogens and diseases continue to challenge crop protection efforts at the local, regional, and global scales. But fortunately, we have epidemiologists working on these problems. And Dr. Larry Madden is a world-renowned epidemiologist, and his work has pretty much defined the modern discipline of quantitative plant disease epidemiology. So it is with special excitement that I am pleased to welcome Dr. Madden to our Botany and Plant Pathology seminar series. Dr. Madden is a native of Pennsylvania, and he received his bachelor's, master's, and PhD from the Pennsylvania State University. He joined the Department of Plant Pathology at the Ohio State University in 1980 and was appointed Distinguished Professor of Plant Protection in 2008. I actually met Dr. Madden in 2006 when I took his popular 702 Plant Disease Epidemiology course when I was a master's student at Ohio State. So I can tell that his work is unique because he has been able to merge basic research on epidemics mathematical aspects with applied research to answer agricultural problems. He has been at the vanguard of using meta-analysis, mixed models, and non-parametric analysis in agriculture to address problems in plant pathology. I can also tell that his early work has served the new generation of scientists who are now building on his pioneering work. And one example, scientists in my lab have recently benefited from his early work on developing, applying, and evaluating proper statistical methods for estimating and comparing epidemics. Dr. Madden's research has been extremely prolific. He has been an author or co-author on more than 260 refereed articles, 20 book chapters, and he's an author of the two main textbooks in epidemiology, one written in the 90s and another in 2007. And his publications have been cited more than 20,000 times as reported today in Google Scholar. And without further ado, please join me in welcoming Dr. Larry Madden. Dr. Madden, it is a pleasure to have you here. Thank you for joining us.
Thank you very much, Christian. I appreciate the very nice introduction. I'm really glad to be back, at least in quotes, back at Purdue. Gave a seminar in your department in Lilly Hall, I don't know, at least 20 years ago, maybe it's even 30 years ago now. I've been on the campus a couple other times since then, but this is, I think, my first seminar since that time when people like Rick Lattin, Greg Shaner, and many others who I've known a long time were still active. So I appreciate the invitation to be speaking today. And hopefully you can see my screen. Christian, can you see it?
Yes, we can.
Okay, good. Let me just adjust my screen here a second. Give me a second here. All right, so today I want to talk to you a little bit about some aspects of our work in plant disease prediction. This is one of the areas that I've spent a lot of time on in the last 10 to 20 years. And I'm just going to hit a few highlights and some of the work that we have not published on in the last few years and tell you a little bit about, at least in passing, some of the work that we have published on. My emphasis is on looking at cost functions and how making decisions on predicting disease and controlling diseases, how that plays into the economics. I've been in plant disease epidemiology a long time, and over the last half century or so, which is a bit longer than my time, but in the last half century, there's been a lot of advances in my field. There's two broad areas of special importance. One is in theoretical modeling for temporal dynamics and spatial spread, and then developing strategies for control based on this modeling. And then the other area in parallel is predicting diseases or predicting the need for a disease control on a real-time basis using various decision methods, and more recently using Bayesian decision theory. The latter is what I'm going to be talking about today in the seminar, using decision theory to look at strategies for disease prediction. This aspect of the work involves my collaboration with Neil McRoberts at Davis, Gareth Hughes in Scotland, and the work on specifically predicting one disease is with Piers Paul and Eric DeWolf. Both of those were my former postdocs. If you want to know a little bit more about Bayesian decision theory, an article published just a few years ago with Neil McRoberts in Phytopathology will give you some background. An old colleague of mine, Chris Gilligan, wrote a number of years ago now that of all the benefits of mathematics in epidemiology, prediction stands foremost. And I think that's a very good motivation for a lot of what I do for research and a lot of what I'll be talking about today. So what do I mean by disease prediction? It means predicting an outbreak of disease or perhaps just an increase in disease intensity. That can be based on the weather, crop conditions, like crop phenology, the pathogen, like inoculum density or behavior of vectors in some cases, or it could be a prediction of the need for a control intervention, spray or not spray, harvest early or not, that type of thing. Synonyms for my purposes are disease forecasting, disease warning, disease risk prediction, and other terms as well. Prediction systems for plant diseases have been around a long time. There were early efforts for potato late blight and apple scab going back a century, really, for deciding when and when not to spray fungicides for diseases like that. But there's been a lot of advances in the last 15 years or so. Some of those involve using machine learning, which we're working on, but I'm not talking about today. And other areas involve using formal decision theory and some Bayesian principles. And that is what I'm talking about today. What I'll be bringing up will give a sense as to why predictors for controlling disease are used or accepted or not accepted in many cases. And I think that should become clear as we go through with the seminar. In terms of plant disease prediction, their success depends on many things. And I list just some of them here. There are others. Only some of these are traditionally considered by epidemiologists. And I'm going to be talking about some that are not traditionally considered. Success depends on how common epidemics are or how common it is that one needs to make a control intervention, like a fungicide spray. Depends on the accuracy of the predictor. That's common sense, of course. The ability to measure the input predictor variables, whatever they are, like relative humidity, rainfall, et cetera, on a real-time basis. The ability to deliver those predictions to the user in a timely, understandable way and in an economic way. The ability to implement a control tactic, like a fungicide, in the time allotted. And then the economic impact of using the system in terms of false positives and false negatives. The three arrows, these 3 points are what I'm going to be talking about in the seminar: commonness, accuracy, and economic impact and cost. My case study will be the disease that I've been working with heavily since the late 1990s or so. It serves as an example that could be used for many crops. There are multiple disease prediction systems developed, both in North America, the US, Canada, and several in Europe, and other work in China as well. I'm focusing on the national system developed by us, the collaborative work by Ohio State, Penn State, and Kansas State, funded by the US Wheat and Barley Scab Initiative. Fusarium head blight, known as scab or in Europe as ear blight, caused by Fusarium graminearum and some other Fusarium species, but primarily graminearum in the United States. Although the disease results in reduction in yield of wheat and of barley, it's of most importance because of the toxin accumulation, which is a mammalian toxin, deoxynivalenol or DON. And that's what gets the most attention in an economic sense. As a matter of fact, the USDA a few years ago declared that Fusarium head blight was the most costly disease of any crop in the history of the United States since the 1950s, once stem rust or wheat was put under better control. Head blight is a monocyclic disease, which means there's generally, most years, one infection cycle where wheat heads become infected around flowering. Epidemics are driven by inoculum, both conidia and ascospores that develop and are dispersed in the spring. There's a long history of work on head blight going back to the early days of the 1900s, almost a century ago. Famous E.C. Stateman and Christensen and others worked on the disease. And they showed early that it's a sporadic disease. Some years the disease is very high, other years it's very low, with differences in varieties. Historic data in Ohio confirms that. Over 50 years of evidence from Ohio showing high and low years. In Europe, the same thing. 2 years as an example. The second year, virtually no disease found. The year before, pretty high. But even in the high year, some fields are virtually no disease and other fields very high. So it's a sporadic disease. And as it turns out, and hopefully this will become clearer later in the seminar, this makes head blight an ideal candidate for plant disease prediction. It's not so common that one always needs to use a fungicide, yet it's not so rare that one can ignore it. We'll come back to that. So head blight in any given year depends on a lot of things. And basically what happens over an entire year in some sense could be influencing the disease. This is sort of a timeline over the course of a year, not drawn to scale. So for a given year, what happens the previous year, how much inoculum infests the weed and corn debris the previous year could in principle have an influence this year. How much of the inoculum from the previous year survives the winter. And then in the spring, how much new inoculum is produced, and how much of it is transported by dispersal, by rain and wind to weed heads. Flowering, infection occurs at flowering, so what's the probability of inoculum that reaches a head in actually causing an infection? And then how the environment affects the colonization of the head and the fungal production of DON toxin. So all of these things can matter, but most of the evidence, including the most recent evidence that we and others have published, show that timeframes right around flowering are most informative for making predictions of disease. In other words, 30 days before flowering when infection occurs, to maybe 20 days after flowering. And in terms of practical times for making a decision for management, flowering is the ideal time to make a prediction, because that's about the best time to apply a fungicide. If you wait more than 6 days or so after flowering, a fungicide does not do very much good at all. So you have to make your decision right around this time, even if conditions later can influence the results. The current prediction system that we developed and use nationally is based on logistic regression modeling. So let me tell you just a little bit about this without going into details on logistic modeling. Basically, the approach is the logit of the probability of an epidemic. In other words, probability of the need to control with a fungicide is a function of some predictor variables. In the simplest sense, it's a parameter coefficient times one predictor plus a coefficient times another predictor, such as relative humidity, temperature, etc. So that's essentially what a logistic model is. Over the last several years, going back to the early 2000s, we've had several generations of logistic models that we've used, starting with using information from 50 location years to most recently, essentially 1,000 location years over multiple states and years. What I'm not talking about today, that's a different seminar with a lot more statistics, is our efforts on the details on logistic modeling, efforts on using modern or contemporary approaches for cross-validation to determine model performance, different so-called regularization methods to prevent overfitting, especially using the lasso method most recently. Ideas on using model ensembles, averaging models, something called super learning. That's hot in machine learning right now. Other aspects of machine learning like boosted regression trees and functional data analysis. And if you do any Google search for papers by Shaw et al. From our group, or DeVolt Wolf or myself, you can find all those papers. Logistic model might seem complicated, but essentially the national system is based on average relative humidity over a 2-week period up to flowering. And basically the probability of an epidemic for the high risk is a logistic function of relative humidity. And once this probability gets high enough, we predict a high risk, and depending on what variety is grown, spray or not spray. The national system, well, first of all, the website changed this past year. I did not update this slide to show you the way it looks right now, but so it looks a little bit different. But it's a national system available free to all users. At any time, one can get a risk map for the United States. One has to know the flowering date, or approximately the flowering date which you put in, and you choose the susceptibility of your wheat variety, your cultivar. You can zoom in, and if it's red, high risk, and if it's susceptible, you would spray. This system has evolved with different models over the years, but I consider one of the things I'm proudest of in my very long career in plant pathology, involving Eric DeWolf, Pierce Paul, both professors and former postdocs of mine, but both professors now, and also climatologists at Penn State. Some recent work based on surveys of users show that the system has an economic value of somewhere between $50 and $170 million a year in the United States. So disease prediction. Let's get back to the main theme of the seminar. I said 3 things I want to talk a lot about today and emphasize how the interplay of these 3 matter. And that is how common epidemics are, how accurate a predictor is for the epidemics, and the impact of using the predictor, the economic impact. All right, so how common or prevalent are head blight epidemics? Well, in the data set that we use from the United States for developing the predictor, 30% of the location years are classified as epidemics. We call that E as an epidemic plus, classified as epidemic. What that means is that's 0.3 is an estimate of the probability of an epidemic occurring, or the probability of high enough level of disease that one would normally think that a fungicide application would be needed if other controls weren't being used. That also means that 1 minus that, 0.7, is the probability of no epidemic. This can be considered the prior probability of a scab epidemic, prior probability. This is independent of any predictor system. This has nothing to do with predicting disease. This is just an estimate of how common the epidemic is. Actually, more recent information I would say the probability for the country is probably more like 0.25 or so. Important thing to point out though, and I'm going to come back to this, is that this prior probability depends on the location. This is sort of a national number. In North Dakota, that prior probability would be higher, probably 0.5 or higher, like half the time, where in Western Kansas, it's probably 0.1 or so, much less common. All right, so let's talk about predicting the epidemic with logistic models. Whenever the logit of the probability of an epidemic, based on the weather, like relative humidity, is above a threshold, we predict an epidemic. So P is from predict and plus. So we're predicting an epidemic. If it's below a threshold, we predict no epidemic. So we have 2 possibilities there. So at the simplest level, there are 2 possible decisions, epidemic or no epidemic prediction. And each of those predictions could be correct or incorrect, which means there's 4 possibilities, right? So we have epidemic, yes or no, prediction, epidemic, yes or no. That gives us the 4 outcomes: true positive, true negative, false positive, and false negative. These are terms that are used in basically the same way in diagnostic testing. And what I'm talking about for the next few minutes has a lot in common with diagnostic development of diagnostic methods and the testing of diagnostic methods. There's extra complexity in disease prediction, but I won't get into some of that. So a true positive is predicting an epidemic when the reality is an epidemic. We'd say that predicting, P+, given that it's actually an epidemic. So that's conditional on being an epidemic. True negative, predicting no epidemic when in reality it's not an epidemic. And then predicting an epidemic when it's not an epidemic, et cetera. The 2 types of mistakes: false positives and false negatives. A false positive is predicting an epidemic when it's not. And the very important mistake that predictors can make is a false negative, predicting a non-epidemic when the reality is an epidemic. So that's a lot to say in a mouthful there, but all those 4 are important. So the initial goal, not the final goal, as I'll come to later, the initial goal is to obtain a high number of true positives and true negatives, or a small number of false positives and false negatives across a whole population. So let's think about a population of results. The 4 possibilities, here are the first 2. If you have 100 or 1,000 location years, whatever you have, and one wants to evaluate them. So you can get the true positive proportion, which is commonly known as sensitivity, the proportion of the known epidemics correctly predicted, and the true negative, or specificity, proportion of the known non-epidemics correctly predicted. And then the sort of the reverse or inverse of that, false positive proportion and false negative proportion. This would be, as an example, proportion of epidemics incorrectly predicted to be non-epidemics, etc. These are interrelated. If you know one of the diagonals, you can get the other diagonal using algebra. So you can get these from the dark blue, or from the dark blue, you can get the light blue. That's a very easy thing to do. Each of these are estimates of so-called conditional probabilities. For instance, TPP, true positive proportion, is an estimate of the conditional probability of predicting an epidemic when in reality it is an epidemic. Same way down here, true negative or specificity is an estimate of the conditional probability of predicting no epidemic when in reality it is not an epidemic. So these are all probabilities, and we will use that in a few more minutes. The data set I'm using to demonstrate all of this in the seminar gives me these results of 124 location years, which is not our final data set. We're actually, as we speak, developing new models for our 1,000 location years. But let's just talk about these right now. So 82% of the actual true epidemics were correctly predicted by our logistic model, and 80% of the true non-epidemics were correctly predicted. These 2 are about the same proportion, 82 or 80. In reality, they don't have to be that close. In any other model, these could be fairly different. So about 20% of the other cases there, we get them wrong, okay? Our newer work over a larger data set shows that these numbers are actually now lower than this, but we'll use these for demonstration purposes. Okay, so that gives you a sense of the accuracy, the sensitivity and specificity. And that may seem good, but then the question is that good enough? Is 80% correct good enough for our purposes? I know from experience that's about as good as you can probably get for this disease. It's a really hard disease to control and to predict. But let's look at this from an economic perspective. So the third component that I'm emphasizing here is the cost of prediction. So given the prior probability, which I talked about, and the accuracy, which I'm now going to define in terms of the false positives and false negatives, we're going to look at the expected or average cost of using a predictor, like the average cost over multiple years and locations. And that formula depends, among other things, on the cost of each possible decision. The cost of a true positive, C of TP, C of Tn, the cost of a true negative, cost of a false negative. In other words, how costly is it to miss an epidemic? The reduction in yield, the increase in toxin, the reduction in the price of grain. All these things happen by your failure to control the epidemic because you didn't predict it, that you needed a fungicide. And the cost of a false positive, predicting an epidemic when you don't need to. So that may mean spraying an unneeded fungicide, the cost of applying that fungicide, the labor, and maybe environmental cost of putting a fungicide in the environment that's not needed, all of those things. For simplicity, and it's a good approximation, we're going to assume that there's no cost for the correct decisions, no cost of a true positive and true negative. In reality, for head blight, that's not really true, because even when you apply a fungicide at the right time at flowering, control is not perfect. There is still a reduction in yield, and there still can be some toxin. So there can still be a cost, but compared to the incorrect decisions, it's a lot lower. So it works out for demonstration purposes here to consider these zero. By considering the correct decisions as being no cost or no loss. When I'm using cost, I'm using it in a negative sense. The bigger the cost, the greater the loss in money or whatever. Okay, if these two are negative or zero, then we can take the other two costs of the false negative and false positive and look at their ratio. And that's known in the literature as a cost ratio. The cost of a false positive to the cost of a false negative. And I'm going to elaborate on that in the coming slides. So remember, a false negative would be you would get a reduction in yield, increase in toxin, et cetera. False positive, you would be wasting money on fungicide and applying it and so on. So look at this ratio. A large cost ratio above 1 means false positives are more costly, more impactful than false negatives. That means there's a lot of expenses in controlling a disease that doesn't matter that much. In other words, this would be a cost ratio above 1 would be for many of the minor diseases. You know, a crop in any given crop in any given location, one could find a lot of diseases, different leaf spots and soil-borne pathogens and so on. Only some of them really matter and have to be targeted for active management. Those that don't have to be actively managed, those are the ones where the cost ratio is above 1. It's more costly to try to control them than anything you gain from that control. You're basically wasting your money. Now, cost ratios below 1, those are the ones that are impactful. False negatives are relatively costly relative to false positives. Big impact of disease on yield, on toxin, etc. Okay, the major diseases in a region fit this area. So we're going to be basically talking about cost ratios less than 1. So why do I even introduce these two costs as ratios? I do it because we no longer have to worry about units. We no longer have to actually know the actual cost. We just have to know how important false positives to false negatives. We don't have to have a dollar value per acre, per hectare, per state. We just have to know the false negative 4 times more costly, 10 times more costly, or whatever. It gives us a way to strategize in terms of looking at the advantages and disadvantages of a prediction system that could be used, okay? And so we'll elaborate on that. For many slides, I'm going to use a cost ratio of 1 to 4 or 0.25. That, missing an epidemic is 4 times more costly than predicting an epidemic that doesn't happen, okay? It's for a head blight, it's probably more like 1 to 5, maybe 1 to 10. But I'll show you those results also. it's easier to see in graphs using one form. So this average cost of using a predictor, there's one formula that's here. I'm going to reduce or eliminate a whole bunch of terms, and I'm going to show you this. I can't do seminars without showing a few slides. Those of you in plant pathology who've been to my talks or have taken my course know that. So we have the expected or average cost of using a predictor. So what are the terms that matter? Overhead cost. This could be the cost in our national case of the cost of running the national system, the website and the labor that goes into running that website. To the end user, that's basically zero. It is zero to the end user. Taxes pay for that in terms of grants. We're going to assume that's zero because it's small compared to everything else. In red are the costs of the true positives and true negatives. By the way, I write this equation like this on purpose. This expected cost is a sum of terms. Each term is a product of three things. Some aspect of the accuracy of the predictor. That's the first column. True positive, false negative, and true negative. All right. So these are all different ways of looking at accuracy. And then the next column, these are the cost of each of these decisions. Cost of a true positive, false positive, etc. And then these are the relevant probabilities or prior probabilities of an epidemic, of a non-epidemic, epidemic, and non-epidemic. So these are all here. I add all these up. I won't derive this mathematically or heuristically, but it's like this. So those in red, these would be the cost of the correct decisions. And we're going to make these zero because we're going to assume from the previous slide that there is no cost in a true positive and there is no cost in true negative, that these are zero. And then in the dark blue, these are the cost of a false positive over all the location years, and these are the cost of a false negative over all the location years. So by getting rid of all the zeros in here, we end up with a simpler equation with these terms. And you don't even have to worry about trying to memorize the equation. I'm going to show you graphs as to what this equation looks like in a range of conditions. And the graphs are what matters in terms of looking at this intuitively. So this equation at the top, this is the same equation at the bottom of the previous slide. And what I'm about to show you has a lot to do with some pioneering work in statistics and biostatistics outside of plant pathology by Biggerstaff and Hilden and Glashow from a couple of decades ago. And there's been a lot of papers since then, but these are the primary papers that got a lot of new work started. So we're going to use this equation and look at a few conditions. We're going to look at prediction in a few settings. We're going to look at this graph in several ways by taking things away and adding things to it, especially adding things to it. So it's very important that you understand what this graph is showing you here. The x-axis is the prior probability of an epidemic. You can consider this like the prior probability of needing to control a Fusarium head blight at a given location. So you can almost think of it as a surrogate for where you're at in the United States. If you're in the Red River Valley of Minnesota and the Dakotas, you're over here on the right-hand side somewhere, maybe in the middle to the right. Epidemics of head blight are pretty common, so the prior probability is pretty high. If you're in Western Kansas, you're way over here on the left, where epidemics of head blight don't occur very often. If you're in Ohio, you're probably sort of around 0.2, 0.3. Indiana also in this range as well, kind of right in this area. Okay, so think of that as an area. The y-axes in red or blue are the costs of using a predictor. But these two that I'm showing you now, these two lines, are predictor that I haven't talked about yet, but I will in a minute. These are the cost of any prior, how costly is that predictor based on its accuracy in the long run, okay? So we look at these lines. Remember, because I'm dealing with a cost ratio, I can do one other thing. I can not worry about actual dollars here. I can just simply say the maximum cost of a false negative is 100%, whatever that is in dollars. That's the maximum loss that could occur from a false negative because I'm dealing with ratios. That means the cost of a false positive on the red will be automatically the same as the cost ratio. I'll explain that in a little more detail with my first example, with my second example. Okay, so that's the background in using this graph. And remember, for demonstration purposes, I'm assuming cost ratio of 0.25. All right, so let's look at the two things that you would normally not think of as predicting or forecasting disease. What if I make a decision always predicting no epidemic? So that is like one type of naive forecasting system. In other words, I'm always going to ignore head blight, that I'm never going to try to control it. I'm just going to just plant the variety I want and live with the consequences, all right? So that's one type of forecast. Basically, that's using a forecast with a false positive of 0. You're never getting, you're never falsely predicting an epidemic because by definition here, you're never doing it. But you're getting all the true epidemics wrong. 100% false negatives is 1 as a proportion, or 100% of all the true epidemics, you're wrong. If you plug in 0 and 1 in the overall equation, you get this, and we get this blue line here. So let me explain this. If you're somewhere where head blight never occurs, never predicting it is the best decision you could possibly make. Your cost is 0 here. But though, look at, as you go to areas where the disease is more and more common, let's say where it happens half the time, where half the time this naive forecast is right and half the time it's wrong. So you're getting a cost of half of the maximum. And of course, if you were somewhere where head blight matters every year, you're getting the maximum possible loss over here, right? Okay. Let's look at the opposite type of naive forecast. That's always predicting an epidemic, always applying a fungicide at flowering, no matter what. That is, you're never, okay, so there you're never getting the non-epidemics, well, you're never getting the epidemics wrong because you're always predicting them. So because you're never predicting a non-epidemic. You're always assuming it's an epidemic. So the false negatives are always 0. There's no false negatives. And that's a good thing. But you're getting all the epidemics wrong. Or you're getting all the non-epidemics wrong. All the true non-epidemics are being predicted as epidemics. You're getting them all wrong, 100% wrong. Look at this with the red line here. But it's easiest to start over here. If you're at an area where epidemics always occur, you would be over here. And now, so always predicting an epidemic is the right decision. No loss. It's 0 here. But then as you're using this rule, this decision, in areas that the epidemics are less common, you're getting more and more cost because you're applying fungicide when you don't need to. So you're getting higher and higher. And if you're taking this rule with this decision where epidemics never occur, you're getting the maximum possible loss over here. But with this decision of always assuming an epidemic, it's not the maximum, it's the cost ratio of 0.25 because it's less costly to apply a fungicide than it is to, when you don't need it, than it is to miss that fungicide when you really do need it. Okay, so that you're not losing as much by taking this decision when the cost ratio is 0.25, okay? All right. So one can call the optimum naive forecast. This is not a plant disease term. This comes from biostatistics. An optimum naive forecast always choose the decision that gives the lowest line in this graph. So from 0 up to 0.2 or so, it's the thick blue line. That means always predict no epidemic. And from this point on, always predict an epidemic if you have no other information. These lines cross based on a property of the cost ratio. And you could say if the prior probability is less than this function, which is right here, predict no epidemic. Above that, always predict an epidemic. One can do this exercise for any disease, any crop. All right. This has nothing to do, this is always with a cost ratio of 0.25. the lines would cross at a lower point with a smaller cost ratio. Now let's talk about the prediction system that we care about, the one for headlight. So we're going to have a third line on this graph. One has a third line based on the cost equation. So we get back to the expected cost, this function, and we plug in these values for false positives and false negatives. So we get a third line on here. So we have a graph with 3 lines. The blue and the red are the same as before. And then the black solid line is, or sort of solid, is actually not quite solid, is for the predictor. And that is simply derived by plugging in the accuracy numbers into the equation. And it crosses the other 2 lines at different places, which I won't get into. So here is the idea of this. By the way, this graph is called a regret graph. Always choose the decision that gives you the lowest line at a given prior. So depending on the prior, it may be better to use the predictor from here to here, or it may be better not to ignore the prediction system that we have and ignore the disease, or to ignore the prediction system and always spray the fungicide, say over here. So looking at the same graph again, these 2 circles show the area where, given everything I've told you, the best decision is to use the predictor, make your decisions based on it, when the prior is somewhere between 5%, 0.05, and 55%, as described here. Outside of that range, it's better to either always spray with a susceptible variety or always ignore the disease. Why? Why is this? Because let's look on the right-hand side here. If you're using the predictor, some of the times there's going to be false negatives. Those become too costly overall when the epidemics are common. So it's better to just spray. Way over here on the far left, there's going to be always some false positives, right? And those are not going to be needed overall, at least on average. So it's better to ignore that and simply ignore the disease. All right. It gets complicated with 3 lines to make a decision on what's best to do. Briggs and Rubert, some biostatisticians, and Briggs and Zaratetsky developed something called a skill or value function that allows us to combine these 3 solid lines. And that value function is simply looking at the optimal naive forecast. Always predict epidemic versus no epidemic versus the predictor, and comes up with a function that allows us to combine all 3 lines. And that's the skill or value here. This function crosses the priors at 2 places, exactly where these 2 circles are. Anything where this function is negative means it's better to ignore this predictor. Anything between here and here, economically, it's better to use the predictor. And the best place to use the predictor is locations where about 20% of the time epidemics occur. This function could be as high as 1, which means we need a more accurate prediction system to get maximum benefit. So there's room for improvement, which we have not achieved yet. This function could be as high as 1. All right. This is what we've been showing so far. What if the cost ratio was 1? Both types of costs, both types of mistakes, both types of errors are equally costly. So what you see is these 2 lines cross at a different place, and the prediction line crosses at a different place. It's easier to see the value function. This is what I showed you before. If the cost ratio is 1, the whole area is shifted to higher priors, and there's a wider range of conditions where the forecaster is more beneficial. The opposite occurs too, which I'm not showing you here. In other words, if the cost ratio is say 0.1, everything gets shifted to the left, where the forecaster or predictor is better only at lower priors and over a more narrow range. So how do we put all this together? We need, for a given disease prediction system, in other words, for a given set of accuracy, true positive and true negative, which is the same as sensitivity and specificity. What are all the combinations of cost ratios and priors that gives us a beneficial prediction system? So we get these contours, different cost ratios versus priors. Remember, the lower the cost ratio, the more costly a false negative is to a false positive. So the most serious diseases would be the lowest cost ratios, way down on the lower left here. And these are the various priors, the same as before. All these areas in black are areas where, with the given prediction system we have, it's better to ignore the predictor. Over on the right, this black is because the false negatives are too consequential. And this black over here, the false positives are too consequential. The lightest area sort of in here, the forecaster has the greatest benefit. Okay, so this is what we were dealing with all along, a cost ratio of 0.25. So we can say from here to here, from about 0.5 to 0.55, this is where the forecaster is beneficial, is beneficial. But what if the cost ratio is 0.1, which may be even a bigger, maybe more realistic for headlight. In other words, those false negatives are more consequential. As you can see, there's a less of a range of conditions, geographic and year conditions, where the forecaster is beneficial. So this arrow is not as wide and is shifted to lower priors. That is a consequence here. So we can look at that. We can look at the other way. We've been dealing with a prior probability for the country of 0.3. So a very wide range of cost ratios, the predictor matters or is beneficial, from above 1, which I have cut off here, down to about 0.07 or so. All right, pretty wide range of cost ratios. But what if we shifted to a lower prior? We were trying to use the forecaster where maybe only 1 out of 10 years headlight matters. And should the forecaster be followed? Well, I would argue only for if the disease is very consequential, a lower range from about 0.4 down to 0.05, under less of a range, but a pretty good range, okay? So we can strategize using all of this information. But what if we had a different forecaster system? We can put a fourth line on here. All the lines are the same except for the brown line. This is a hypothetical new predictor that we have not developed yet, but let's pretend has a sensitivity of 92% and a specificity of 90%. That would be really nice to have. So that's this line here. Notice it crosses the other lines closer to 0 and closer to 1. So instead of this value function here, we have a more wider value function. So the forecaster would be beneficial at a lower prior and a higher prior. We can look now at and this is at a cost ratio of 0.25. At the full range of cost ratios, we can see that almost the entire area is outside of the black now. So there's only a much more narrow range where disease is extremely common. And I don't think there are any areas where 9 out of 10 years, the epidemic, this disease matters. So it probably doesn't really matter here. So almost anywhere that would mean the forecaster is better than not following the forecaster. So we can do more and more of this. And this is just give you an idea of my active research right now. So just to conclude, disease prediction or forecasting, I would argue, is a valuable applied outcome of basic plant disease epidemiology. Predictors can be developed with a wide range of methods. Our method of choice is some aspect of logistic modeling, but there's many other approaches that are valuable, from machine learning to back of the envelope calculations. I'd like to remind audiences, and I like to remind epidemiologists, prediction is difficult. Niels Bohr, a famous physicist, said a prediction is difficult, especially about the future. This quote has been attributed, probably falsely, to others, including Victor Borge, a comedian, to Yogi Berra and others. But I think the physicist first said it. The point of my seminar today and some interrelated things has been an argument for Bayesian decision theory and Bayesian decision thinking in terms of the evaluation of predictors. Metz, Hilden, Biggerstaff, and others. These are people in biostatistics that have a big influence in this area. In plant pathology, Jonathan Ewan, Fabre, Gareth Hughes, Neil McRoberts, Bill Turchak, Peter O. Giambo. My direct colleagues, Piers Pollan, Eric DeWolf, and others have all made major contributions here. And in my seminar today, I've been trying to combine these. My take-home message is the prior probabilities, cost of making decisions, and accuracy of forecasters or predictors all should be integrated in terms of looking at forecasters to look at expected cost. So I would argue instead of the final goal to be coming up with a highly accurate forecaster, which is certainly a good intermediate goal, a better final goal is to develop a predictor that minimizes regret or maximizes the so-called skill or value for the predictor. And I would say unless the predictor is extremely accurate, one should not always use a predictor, even when one has a predictor. My current work is developing more accurate predictors and more work related to this. So I covered a lot here today. I don't know how much time there is for questions, but I wanted to give you a sense of some of the things I'm working on. So Christian, I'm just going to turn it back over to you and then you call the shots. Thank you. Thanks for your attention.
Thank you very much, Larry. And yeah, so we have time for questions. So Greg has a question here. So he's asking, has there been any attempt to determine what proportion of farmers in different areas use the forecast, different prior probabilities?
We have a little bit. I think you're saying what proportion of people in different parts of the country. We have a little bit of that. We do not have it in terms, well, the greatest information we have is not an official survey sample where we totally try to eliminate biases. We survey the users of the forecasting system and ask their views on the dollar value they think the system is worth to them. A lot of the users are crop advisors rather than growers. The growers themselves who use it, we know from the surveys, are mostly the bigger growers, have more at stake. But a lot of crop advisors use it. A lot of extension specialists use it and then redistribute that information through different avenues in terms of their own websites and Twitter, et cetera, et cetera. So we have that. There has been, but that's not a formal survey sample. Now, the funding through the SCAB forum or through the U.S. Wheat and Barley SCAB initiative, there's been more recent official survey samples of the benefits of and the use of this system, as well as other sources of information, where the national website for just information on cultural practices, rotation, varieties, all of those things, testing for dawn, all those things. So we're getting more of that information, but I can't say its use. Anecdotally, though, I would say the biggest use would be the highest impact area, certainly in the Northern Plains, the Dakotas, Minnesota, but a few other states, Illinois, et cetera. A lot of it depends on how engaged the state specialist, extension specialist is in advertising the system. Okay.
Fantastic. So I have a question also. So you mentioned that sporadic diseases are ideal candidates for prediction. And the question is, so how about those diseases that occur year after year, especially in tropical areas? And especially when you're looking into calculating cost versus prior probability. So how can you validate?
Right, okay, that's a very, very good topic. The same idea applies, but we have to shift the time scale for that. And we don't even need tropics. We can talk about apple scab in the eastern half of the United States. Now, we haven't applied and no one has applied these concepts because there's some other complications that I won't get into here. Now, the eastern United States, if you look at the time frame of a year, apple scab matters virtually every year. There's a few exceptions, but maybe 90% of the years, on the year basis, apple scab really matters and you have to control it. almost all apple varieties grown commercially are highly susceptible to scab, so to apple scab. So you have to apply fungicides or biocontrol products or whatever. But that's not the time frame that matters for that disease. That time frame is on a daily or weekly basis. On that basis, every day is not a high prior. The prior probability on any given week, say, is probably a lot lower than that, less than 0.5. And if you move your time frame to a daily, like the Mills forecasting system is applied on a daily basis, basically. In that time frame, the prior is 0.3 or so 0.4. So it is kind of this, it is sporadic on that time frame. So therefore, you don't always have to apply a fungicide every week, for instance, but you can't always ignore it either. So it's somewhere in between. So it's also, once again, sporadic. So it's a good candidate. Yeah, so you have to make that kind of switch. And that would be true for tropical diseases too.
Right, and so if you look at this scenario, for example, there are also cycles where you won't have epidemics, but the majority of times you will have epidemics. And so if you're comparing epidemics versus non-epidemics, so it's kind of like it's not a normal distribution what you're seeing there, and so it's skewed very much. And so you're going to have less years and less data points for non-epidemics years. So how likely is it going to be for you to determine whether that's accurate or not?
Well, that leads directly into the mechanics of even being able to develop a good prediction system. You need, obviously, a data set or data sets that could be of different forms. That can be simply empirical, which is mostly what we're using, which is not the only approach. In other words, having lots of hopefully unbiased data on the intensity of the disease, or it could be based on toxin or whatever for a wide range of locations and years, and a wide range of environmental conditions. So you have a pretty good distribution of the range of conditions that lead to epidemics and to non-epidemics, or that leads to high disease versus low disease and everything in between. You need that. Other types of data that you could use instead of that would be based on controlled studies, more mechanistic modeling based on the conditions that you learn from a growth chamber. What are the combinations of temperature and moisture that lead to infection or colonization or whatever, and then developing a simulator that actually puts all that together. That's a viable approach as well. And there's prediction systems, like that. So, but you need enough range. And in our case, we have about a quarter of the data would be what we call epidemics, or the need to control the disease. One can argue about that. If our data set only had 5%, it would be much harder. It would have been very hard for us to develop a prediction system because there just wouldn't be enough data on the epidemic side. Or if it was 90%, 95% epidemic and only 5% non-epidemic in our training data set and testing data set, that's what we had. We would have a very hard time developing, not impossible. There's just bigger challenges. You just need more data then. If you have a very small percent of epidemics or a very small percent of non-epidemics. So those are all the challenges in developing the prediction system. Those are all very, big challenges. That's not exactly what you were asking, but it's kind of, what I was, some of the things that we in statistics and in epidemiology have to deal with. And if you could just give me one other 30 seconds here, not exactly an answer to your question, but I just thought of it in my other answer, and I didn't say this specifically in the seminar, but a motivation for this new work by me on the expected cost has to do with something that plant disease epidemiologists have often brought up over 40 years that I know people. There's been many plant disease prediction systems developed on all kinds of crops all over the world for a century, or so. Epidemiologists also always or often lament the fact that developing a system that works in test cases, but growers don't use them, or they ignore them. And there's lots of reasons to ignore them. And that early slide I show about many of the reasons for success of a forecaster, all those things matter. It's not just having an accurate forecaster. You have to be able to deliver the information. The information you give a grower has to fit into their system. They're busy during the time they need to control a disease. It may be a lot easier to just, apply a fungicide, even though it costs them money. So there's all kinds of, issues like that. These three things where I put together that it's more than the accuracy. It has to do with prior probabilities, and it has to do with the cost of the incorrect decisions. Unless you have a perfect forecaster where there's no incorrect decisions, which you could say doesn't exist, unless you have that, all these things simultaneously combine. And what I try to do is give a way forward to think about reasons why a forecaster might be adopted in the industry and why it might not be. Okay.
Fantastic. Thank you for the answer. Yeah, so those are the questions that we had. So I think we still have time. So if you wanted to present something else, it looks like you wanted to show something.
No, I don't need to show. I mean,
okay.
I can show 150 slides to you, but I think you've seen enough to get my take-home message.
Fantastic. So great. So well, with that, thank you very much, Larry, for joining us today, and I look forward for the discussion after this seminar. So
sure, I'm just going to stay on this
yes.
link. Okay. Okay, good. See you all. Thank you for your attention.
Also, thanks to Amy for helping us organize this meeting. So,
yep, thank you.